Today we are going to discover what the Earth is made of and how it continually changes. We'll also learn about the kinds of rock that form the Earth. And lastly, we'll go in search of a treasure that has become indispensable to our modern societies: oil. The study of our Earth isn't as simple as you might think. First, you have to constantly adjust to changes in scale, taking into account both the infinitely big and the infinitely small. For example, a crack only a few millimeters wide in the Earth's crust can cause a seismic shock extending through thousands of kilometers of terrain. The same is true of the geological timescale. Some events, such as earthquakes and volcanic explosions, are sudden or violent, whereas others, like erosion, the formation of glaciers, or the continental drift, take dozens, hundreds, even millions of years. Today, there are many different techniques for gathering data on the makeup of the Earth at various depths. The most useful is seismology, which is the scientific study of quakes and the phenomena associated with them, namely earthquake shocks. By studying the trajectory of seismic shocks, experts have been able to define the Earth as we know it, a sort of ripe fruit. Over the past century, man has made many discoveries about the Earth's internal structure. This newly acquired knowledge has enabled us to draw a parallel between the Earth and an apple. Earth is made up of a core and a peel, which never stop twisting, folding, and cracking. The Earth is divided into 4 main zones. The inside core, with a diameter of 3,500 kilometers, is about the same size as the planet Mars. It mostly consists of iron and nickel, and its temperature fluctuates between 4,000 and 5,000 degrees Celsius. However, even at such high temperatures, the core remains hard because it is subjected to pressure weighing some 3 million atmospheres. Around the solid inner core is an outer core which is liquid. The third zone is what geologists call the mantle. There is constant movement in the mantle. The high temperature of the core heats up the bottom layer of the mantle. This makes the mantle less dense, and it rises to a top layer where it cools down. As it cools, the substance resumes its density, and force of gravity pulls it back to the bottom. This is the principle of convection. Scientists believe that a series of convection cells form inside the mantle and cause the lithosphere to crack and fold. The lithosphere comprises the mantle's crust and rigid layer. Faults divide the lithosphere into enormous plates called tectonic plates, which fit together in a complex mosaic formation. The plates consist of pieces of continental and oceanic crust. Beneath the lithosphere, there is a molten matter called magma, which forms in the mantle and exerts tremendous pressure. The faults separating the plates constitute weak zones in the Earth's crust, and magma erupts through them. It is therefore not surprising that most of the active volcanoes are found in these areas. Scientists believe that about 200 million years ago, all continents were joined together to make one supercontinent called Pangaea. The pressure of the movements of the Earth's crust caused Pangaea to fragment into smaller continents, which then began to drift. Molten matter rose up from the depths of the Earth and began cutting the supercontinent up and pushing fragments on either sides of the cracks, forming ridges. The dotted line indicates the exact current position of the mid-Atlantic ridge. Lava burst out through the crust all along this ridge. It then solidified along the edges of the plates, which grew larger and separated. This is how the Atlantic floor widened, separating America and Europe. But where the expansion occurs most rapidly is along the eastern Pacific Ridge, where it grows by an average of 6 to 8 centimeters a year, about the same rate at which a human fingernail grows. In some places, the ocean plate plunges beneath the continental plate, which is lighter and even penetrates the upper layer of the mantle. This is what scientists refer to as the subduction phenomenon. This has occurred all along the east coast of North America. The floor of the Pacific Ocean goes under the continent and delves deep into the magma where it gradually melts. This phenomenon is accompanied by friction and folding, which in turn generate shocks and form mountain ridges. This meeting of plates produces tremendous energy, causing the rocky surface to crinkle like paper. Mountain ridges, volcanic eruptions, and tremors are all a result of these gigantic shifts. To better understand these natural phenomena, various techniques have been developed to measure activity underneath the Earth's surface. Seismic reflection is one such technique, and it provides geologists with information about the Earth's subterranean composition and structure. This is how the technique works. A metal plate is used to make the surface vibrate. The resulting vibrations run through the Earth and are then reflected off a subterranean discontinuity. At the surface, geophones, which resemble microphones, are set up along a distance of a few kilometers. The geophones detect vibrations passing through rocks, soil, or ice. The information is analyzed by computer and then reproduced in three-dimensional form. The Earth is in perpetual motion. This results in a constant shifting of plates, in quakes and volcano activity. The study of these natural phenomena, along with drilling into the Earth, can provide information on the composition of the Earth's crust as well as on its formation. It can also help us develop more refined mining exploration techniques. Earth is like Ali Baba's gigantic cave, chock full of precious metals like gold and silver. Rare crystals like amethysts and rubies, and useful minerals as well like marble, clay, granite. Because we know so little about the Earth's mantle and core, we only exploit the rocks and minerals that make up the thin outer crust of the planet. In a quarry, an amateur geologist armed with only a chisel and a hammer could easily find a number of common minerals such as quartz and mica. But to be able to find rare minerals, he would have to know something about how they were formed over many centuries. The Earth was formed some 600 million years ago. According to astronomers, rocks, dust, and ice particles floating in space collided and stuck together under the effect of their own gravity. It is believed that all the planets in the solar system, including Earth, were formed in this way. Geology is the study of rock formation. Rocks are broken down according to their origin into three main categories. Igneous rocks constitute 90% of the Earth's crust and were formed when molten magma solidified upon reaching the surface of the Earth. Unlike igneous rocks, which come from inside the Earth, sedimentary rocks are formed on continents or in water. As their name indicates, they result from the accumulation and consolidation of sediments. These types of rocks only make up 5% of the Earth's crust, but they occupy more than 3/4 of the surface of continents. The third type of rocks are metamorphic. They are formed from igneous and sedimentary rocks brought into the depths of the Earth's crust and transformed by heat and pressure. Contrary to what you might think, rocks are not necessarily hard and compact. From a geologist's point of view, sand on beaches and petroleum, oil, are rocks. A rock is a natural compound of more than two minerals, such as quartz, feldspar, and gold. But you mustn't confuse rocks with minerals. Minerals are natural inorganic substances that make up rocks. Metals are also minerals, but they are rarely present in pure form in rocks. More often, metals are combined with other elements. Minerals always have the same composition, regardless of where they are found. For example, quartz is composed of silicon and oxygen. Some 2,000 different minerals are known to man, almost all of them composed of crystals. To identify the various minerals composing rocks, geologists have to examine them under a microscope. A rock sample is taken, and it is diced into small pieces. These little cubes are then smoothed out with abrasives. Epoxy is then used to glue them to a cover glass. Next, a cutting tool covered in a diamond powder, diamond is the hardest mineral known to man, is used to reduce the cube's thickness to about 0.03 of a millimeter, about the thickness of a sheet of paper. This process makes almost all minerals become transparent. The mineral sample is then examined under a polarizing microscope, a polariscope. This instrument is fitted with two filters which polarize light. The sample is placed between the two filters. The first filter is a polarizer, and it is placed underneath the sample. And the second filter, the analyzer, is placed above the sample. A white light is placed underneath the first filter. The light shines in all directions. The polarizer, in a sense, filters the light waves so as to let through only those waves moving in a single direction. If the analyzer is placed at right angles with the polarizer, no direct light will go through. However, the crystals deviate the light waves, allowing them to pass through the analyzer. Each mineral has a specific color due to the configuration of its crystals. By turning the cubes around, you can observe the distinctive colors of different minerals. Electron microscopes enable geologists to further their study of rocks. Thanks to the electron microscope, various chemical elements in rocks can be examined. With this system, the sample is bombarded with electrons. The various elements making up the mineral in turn emit electrons and X-rays that produce an image that can be viewed on a cathode ray screen. Once the images have been processed by computer, the elements making up the mineral can be identified according to the different colors that have been assigned to them. This technique allows for a fairly accurate estimate of the proportion of elements in minerals. Among the great variety of minerals contained in the Earth's crust, some are present in the form of traces. In mining, for economic and technical reasons, it is important for scientists to be able to estimate the mineral contents of rocks accurately. For this reason, the polariscope and the electron microscope have become indispensable tools. Man didn't wait for the invention of the electron microscope to exploit the Earth's riches. In the Stone Age, man was already making tools from silex and obsidian. Seems that he used those stones on a quasi-industrial scale. Silex mines as much as 10 meters deep with galleries several kilometers long have been traced back to the Stone Age. Back then, man also searched for gold and copper in riverbeds. He made weapons and jewelry with the metals, decorating them with amber, turquoise, amethyst, or jasper.
Nowadays, we still turn to the earth to fill our needs, since the first oil well was drilled in Pennsylvania back in 1859. The uses for this fuel have continued to multiply around the world. But did you know that petroleum, like coal and natural gas, is organic in origin?
Every year, roughly 3 billion tons of oil are consumed around the world. Known oil reserves are estimated at 120 billion tons. Unless major new sources are found, we will exhaust current reserves within the next 40 years. Oil is a non-renewable energy resource. It was formed over millions of years. Geologists believe it formed from the accumulation on seafloors of remnants of animals and plants, and microscopic organisms living in water called plankton. Over the centuries, these remnants compacted and accumulated under layers of sedimentary rock. Under raised temperatures and pressures, the organic matter turned into hydrocarbons. Hydrocarbons are the chemical compounds of oil and natural gas. Natural gas comes from the transformation of oil at high temperatures. Petroleum and natural gas migrate through rock and have a tendency to rise toward the surface. To form a deposit, both have to be trapped in porous rock, like limestone, called carrier rock. Petroleum collects in pockets formed along the folds in the Earth's crust. Some scientists have another theory about the origins of petroleum. Astronomers believe that the largest reserves of petroleum and natural gas are not organic in origin. They believe that hydrocarbons were already present when the Earth was formed, trapped inside the globe. Supporting their hypothesis is the fact, among others, that hydrocarbons have been found on other planets. This finding was made possible by spectroscopy, which is the analysis of spectra which absorb light coming from other planets. Whatever their origin, these are the oil fields prospectors are looking for. Since most of the continental deposits have already been exploited, prospectors have turned to oceans, a less hospitable environment. To explore the depths of the ocean in the Arctic regions, huge floating platforms were built, measuring up to 100 meters across. Even though they float some 200 meters above the ocean floor, these platforms can drill to a depth of 6 kilometers beneath the Earth's surface. Offshore exploration is particularly difficult in the polar regions. At these latitudes, everything is permanently frozen, and the average year-round temperature is minus 15 degrees Celsius. Icebreakers are needed to tow the platforms to the exploration site. The icebreakers, equipped with 24,000 horsepower motors, plow through the ice at a speed of about 3 knots. As for the platforms, their sides are built at an angle so as to break the ice and shove the pieces out of the way. Once the oil platform has reached the exploration site, 12 anchors are lowered to the ocean's bottom to hold it in place. When an oil field is found, the next stage is to exploit it. Drilling platforms are then installed over each well, and they will remain in place until the deposit is exhausted, usually 15 to 20 years. The huge platforms are designed to be able to withstand waves up to 30 feet tall and winds gusting up to 230 kilometers an hour. There are several types of platforms. The one here, for example, consists of a steel ring weighing 8,000 tons and measuring over 100 meters in diameter. It sits on a sand base made of sand either dragged from nearby marine floors or transported from elsewhere. Technological progress should soon make it possible to exploit offshore oil fields, even if they are located at depths of 1,000 meters.
Alchemists in the Middle Ages believed that the bearer of an opal, wrapped in a laurel leaf, could become invisible. When you next offer a friend a gift, think about it. Some stones may have extraordinary powers.